Alright, welcome back again to our video lecture in ABE161. Okay, so in this video, we'll be doing our first sample problem for the analysis of singly reinforced beam. So in this problem, again, we're saying analysis, meaning that we're given the geometry, we're given the details, the steel area, and we are to determine the capacity. Okay, so the beam has this geometry. The beam width is 270 mm. Okay, so let's write mm, and then the the effective depth is 350 mm, and it's reinforced with 316 mm rebores, and the FC prime, that's the compressive strength of concrete, is 21 megapascals, and the Fy is 275 megapascals. We are asked to find um, the factored moment capacity. Okay, so when we say phi mn, so that's the factored moment capacity, and we are asked to check if the code requirement is met. Okay, so first, recall that our equation that we need is the depth of stress block and then the nominal moment capacity, and then after that we'll solve for the strain value to determine our reduction factor. Then once we know that, okay, let me write down. Okay, so first what we need is the depth of stress block. Okay, so once we know this depth of stress block, then we can solve for the nominal moment capacity, right? So this is A is just simply A as Fy all over 0.85 Fc prime times B. So once we solve this, we can get actually we can now get the nominal moment capacity, because the nominal moment capacity is just A as Fy B minus A all over 2. Okay, so we need the value of depth of stress block because we need it here. Okay, so once we get this, then we have to find the strength reduction factor. But how do we get the strength reduction factor? We need to solve for this strain. So for the strain value, uh, we have to determine this, and we also have to compare compare it with the yielding strain. Okay, so once you have the yielding strain, then you can determine whether you are in transition region or tension control region and stuff like that. So once you have this, then you can determine the strength reduction factor. Okay, so once you have that, you get this. So once you have this strain value, then you can solve for this nominal moment capacity. Once you solve this nominal moment capacity, then we'll just have to check the AS, minimum AS. Okay, so for now, let's solve this. Okay, so we have 316 mm. Okay, so for now, let's solving for AS. Okay, so meaning area of steel. So AS is equal to 3 times, since we have 16 mm diameter rebore, then 16 squared times pi all over 4, which is just equal to 603.19 mm squared. Okay, so now we have this AS, then we can solve for solving for A, that's the depth of stress block. So A is equal to A as Fy, 0.85 Fc prime times B, so which is just 603.19. Okay, so what is our Fy? Our Fy is megapascals, 275 megapascals. Okay, so take note, our megapascals, it's in Newton per mm, mm squared. Okay, so if that's Newton per mm squared, sometimes I don't write the units, but it's also good if you can do so, if you can write the units. So this is in mm squared, is mm squared. I mean Newton per mm squared. Okay, and we have the 0.85, and what's our FC prime? we have 21 megapascals. Okay, megapascals, and our B is this is our B. So 270. That's in mm. Okay, so mm squared divided by m. So we get a unit of mm. So if you compute that, what you get is 34.42 mm. Okay, so now we can solve for the nominal moment capacity. Okay, solve for mn. Okay, so just apply the equation. It's just ASFY times d minus a all over 2. So this is just 0.19 times 275. So 350 minus 34.42 all over 2. So if you solve that, you get an answer of 55.2 kilonewton meter. Okay, so uh, we're actually in mm. If you solve this, what you get is something like, probably what you get is 55, 200. Okay, let's say this is the rounded off value. So that's in Newton mm. So we have to divide this by 1 times 10 to the 6, right? 1 times 10 to the 6. Okay, so because we have to convert that to kilonewton and meter. So kilonewton, that's 1,000, and then meter, that's another 1,000. So 1,000 times 1,000, you get 1 times 10 to the 6. So what you get is 55.2 kilonewton meter. Okay, so you can check if you'd like, but that's just the simplest way. So once you have this in mm and newton, so you get something value, something like this, something this large, let's say large scale. So you just have to divide it by 1 million, or 1 times 10 to the 6, and the unit would be kilonewton meter. Okay, so that's our moment capacity, nominal moment capacity. Okay, so now let's now solve for the strain. So before we solve for the strain value, we need to solve for the depth of stress block. So no, not the depth of stress block, the depth of neutral axis. So recall that we have this equation: A is equal to beta times C. So here, this one is given. This beta can be determined, so we can solve for C. So C is equal to A over beta. Okay, so this one is given. This is 34.42, whereas here we can determine if our strength of concrete is less than 28 megapascal. If it is, then that's 0.85. If not, then we have to solve it. Okay, so C is equal to A all over beta. What is A? 34.42 mm. And what is this stress block factor? So recall that is B is equal to 0.85 if FC prime is less than 28 megapascal. Okay, so we have a 21 megapascal. So we have a beta value of 0.85. Okay, so you can solve this C. You have 40.49 mm. So another way to check is that our depth of stress block is, the depth of stress block must be less than this depth of neutral axis. Okay, so now we'll solve for the strain value. Okay, so say 5. So solving for strain. Okay, so our equation is 0.003 d minus c all over c, which is just simply, what is our d? So our effective depth is 350. So 350 minus our c, which is 40.49. So 40.49 all over C 40.49. We get a strain value of 0.02293. Okay, so the strain value is actually a decimal value, and it's a small value. So here in our course, when we do calculations, we'll just use up to 5 decimal places. Okay, so 0.02293. Okay, so it says here that our strain in the tensions, okay, if we draw it here, something like this. So, oops. So it says here that our strain here is 0.02293, but we'll have to check if it's what's our yielding strain. So E sub y, that's our yielding strain. So E sub y, you can solve for you can solve it if you recall this equation, E something like this, the generalized Hooke's law from your strength of materials. So stresses is proportional to strain by this modulus, or Young's modulus of elasticity. And for steel, this is a constant. So E for steel, this is 200 gigapascals. Okay, so if that's gigapascals, then if you convert that to megapascal, 200,000 megapascals. Okay, so except that in this course, instead of using this sigma notation, we use the F, the small letter F. Okay, so here we can solve it Fy, since we are talking about the steel, then Fy, yielding stress, of course, divided by this E, okay, modulus of steel. So this is 275 megapascals all over 200,000 megapascals. We get a value of 0.00138. Okay, so if you compare that, our strain in the extreme tension steel is greater than, okay, 0.005. Why? Because this is 0.02. Okay, so this is greater than 0.005, which is so far greater than our yielding strain. So meaning our reduction factor is 0.9. Okay, so going back to this illustration, our strength reduction factor over this strain. So if you have a 0.005 greater than 0.005, then you have strength reduction factor of 0.9. Alright, so now you have this. So you can now solve for the nominal, the factored moment capacity. So it's just simply 0.9 times our nominal moment capacity, which is 55.52, 55.2 kilonewton meter. And if you solve that, what you get is 49.68 kilonewton meter. Okay, so this is a reduced value. So instead of using this 55.2 kilonewton per meter, instead of using this value in the design, we're actually reducing it, okay, because of the uncertainties in the strength or the properties of the materials. So we have 49.68. So that's it. Now we have to check the area. So for the area, so AS mean would be maximum of, that's the two condition. We have the square root of FC prime for Fy BD, and then another criteria is 1.4 BD all over Fy. Okay, so if we solve this first condition, we get a value of 393.68 mm squared, and then at the second condition we have value of 481 mm squared. Okay, so just a couple of notes. This is square root of FC prime, so don't bother about the units. So if you put in megapascals, then you get out here in megapascals as well. So don't take the square root of megapascals. Okay, so um, just ignore these square root sign values for the units. Right, so our AS mean, if you recall, we have 603.19 m squared, which means that our AS, is greater, our AS is greater than our AS mean. Therefore, code requirement is met. Code requirement is met. Okay, so just a brief review on what we did in the sample problem 1. We first solved for the steel area because we need that in calculating the stress block, the depth of stress block. So once we solve for the depth of stress block, we can solve for the nominal moment capacity. Okay, so once we solve for the nominal capacity, we have to solve for the strength reduction factor. But in order to solve for the strength reduction factor, we have to solve for this depth of neutral axis. Okay, once we have the depth of neutral axis, we can solve for the strain in the extreme tension steel and compare that to the strain in the yielding strain. And then from there, we can determine the condition of the section, if it's tension control or compression control or something, right? So now we determine, since our strain is greater than 0.005, then that's going to be tension controlled region, and the reduction factor is 0.9. So we just applied here 0.9 times the nominal moment capacity. That's 49.68. Okay, and then we check the AS requirement. All right, so I guess in the next video we'll solve another, or maybe still here in this video we'll solve for another problem. All right. By the way, you can also check. Okay, what we check here in the previous problem is the minimum area, but you can also check for the bar spacing. Okay, so now moving on to our next problem. So we have this problem 270 by 350, the effective depth, just the same with our previous problem, except that I uh, I included here, or I inserted here 10 pieces of 16 mm, and that's in 2 layers. Okay, so at least we can have a feeling on what if we put um, we put um, more percentage of steel, then what will happen to the let's say the strength reduction factor or the moment capacity or something like that. Okay, so now let's solve for the AS. So AS is just simply 10 times 16 squared all over 4, and that's 0.62 mm squared. Okay, so now the next step is to solve for our depth of stress block, which is ASFY over 0.85 FC prime times P. So again, this is just pretty the same with our previous problem, 270, 350. FC prime is the same, 21 megapascal. Fy is 275, except that the number of steel reinforcement is greater. Okay, so A, if we solve A, if you substitute the equation, what you get is 140.73 mm. Okay, so now if we solve for our nominal moment capacity, so D minus A over 2, what you get is 161.8. This is 161.8. This in Newton, I mean kilonewton. It should be in kilonewton meter. Okay, so if you notice in our previous problem, we only have around 50 kilonewton or 55 kilonewton. Okay, so this is our previous problem. We have value of 55.2 kilonewton meters. But if we increase the steel area, then we have an increased capacity. Okay, so now let's solve for the depth of neutral axis. We have A over C is equal to A all over beta, so which is just 114.73 mm. Again, so for our beta, since our FC prime is less than 28 megapascals, so that's automatically 0.85. Okay, so our C is 134.98 mm. Okay, so the next step is to solve for the strain in the extreme tension steel. So we have a 0.003 times 350. Okay, so since we have a two layers, then we have to determine the we have to determine this distance. So let's say we have let's say plus 25 mm. Okay, so let's say 350, or let's just put half. So let's say 365, just for example. So 365 mm. Okay, so if that's the case, then you just have to solve this 365 minus our C. Okay, 365 minus 134.98 all over 134.98. Okay, so I suspect that we will be in the transition region, but you have to check it. Okay, so because my first calculation, I just used the value of 350. Okay, so anyways, if we have this much, let's say much area of steel, then probably will be in a transition region. So if we are in the transition region, so you just have to apply this formula, minus E sub y for 0.005 minus E sub y, right? So you can get this, and then once you have this strength reduction factor, then you can solve for the factored moment capacity. Right, so I guess that's all for now in this video. I'll just leave this up to you, but the process is the same. Okay, so it is also possible for other problems that instead of using a 0.85 here for the stress block factor, we can apply the equations for the stress block factor, especially if we use, let's say, 30 megapascals or greater than 28. Okay, so you just have to apply those derivations or those code provisions. All right. One last thing is I'd like to discuss another parameter in this beam designs. Although we're not gonna use it much here. I mean, we'll just do the analysis problem. But for design problem, this parameter is also very convenient. Okay, so there is another way. Okay, another way to classify the condition of the beam section, and that is through this rho is equal to AS all over BD. So this is what we call as the reinforcement ratio, meaning the ratio of the steel area to the concrete area. Of course, this is just the usable concrete area. So it's not B times the total height. This is just beam width times the effective depth. Okay, concrete area. Okay, so if we try to solve for AS using this equation, we have AS is equal to rho BD. Okay, so now recall the equation A is equal to ASFY 0.85 FC prime times B. So from this AS, we can actually substitute it to the AS here. Okay, if we rearrange this equation, then we can actually substitute it here, or this one, we can substitute it here. Okay, so if we substitute, then what we get is A. Okay, substituting it here, we get rho d Fy 0.85 Fc prime. And since we can recall that also we have an equation A is equal to beta times C we can also substitute that to this equation. Okay, so let's just say here, this equation. Okay, the point here is, after all the substitution, what we get is actually this equation P, or rho 0.85 Fc prime beta Fy, right, times 0.003, 0.0, right? So if you substitute these equations, you'll finally arrive to these expressions, which is a rho as a function of the strain. Okay, so it just means that you can also classify the condition of the beam is, in terms of the still ratio. Now, with respect to the nominal moment capacity, there is also a relationship between the still ratio and then the moment capacity. So that's the derivation is included in our lecture handouts, but I'll just write here the expression, okay, because we don't have much time now. In the next video, I'd like to move on to the next topic. Okay, so that's why. Okay, so this is the expression of the nominal capacity. Sorry, the factored moment capacity of the beam in terms of the still ratio. Okay, so there's still another way to compute the capacity of the beam, and that's in terms of still ratio. But for us here in this course, we'll only uh, we'll only do the ones that we did. Okay, and that's just the basic ones. Okay, so now this expression is, you notice that it's the capacity, factor capacity, as a function of this still ratio. Okay, and if we divide this expression by BD squared, we can actually obtain a graph, something like this, the moment strength, and then we have this reinforcement ratio. Okay, so if we plot this, you'll notice that there is a graph in our lecture handouts, something like this, and then another curve, something like this. Okay, so what it means is that if we recall that this is our section, so if we have less steel reinforcement, if we have less reinforcements, then of course we have fewer capacity, right? And if we put a lot of reinforcement, then of course we're gonna have increasing capacity, right? And that's what we did in our two problems, and we've solved that. Except that for some value of rho, for the nominal capacity, yes. So the more you increase, so let's say this is it, the m sub n. That's the graph, the first curve, the nominal moment capacity, and then this one is the factored moment capacity, right? So once we apply this strength reduction factor, okay, so here you'll see that the more you increase the steel ratio, you'll get an increase in the nominal moment capacity. But if we try to incorporate the strength reduction factor, you'll notice that you can barely have an increase in the nominal, in the capacity, the factory capacity. Okay, so why? It's simply because the more that you increase the, the percentage of the steel, you're actually getting um, into you're getting into a brittle mode of failure or a brittle behavior of beams. So you get a okay. So let's just say here, get a brittle behavior of beam, and hence your reduction factor is 0.65 instead of 0.9. Okay, so that's the reason. So the point here, um, we can actually observe that what we want is actually a ductile mode of failure for beams, because ductile mode of failures gives warning. Again, ductile failure means that there's going to be deformation for the beam before it collapses. So that's probably the reason for this 0.65 or zero point 0.9, just to um, ensure that ductile ductile behavior is probably used or something like that. All right, so I guess I'll leave you to the derivations. I haven't discussed much in the details, especially for this, but my main point of the discussion is just basically this: to understand and to introduce you that the moment equation, you can actually be solved using the steel ratio if you have this. Okay, so in the next topic, we'll be discussing the um, shear reinforcement. All right, so see you in the next video.